Okay, the topic for today is 2D equilibrium of rigid body. Equilibrium of rigid body. What's the difference between rigid body and particle? We already discussed particle. What's the equilibrium of it? And then we found two equations, sum of f of x and sum of f of y equal to 0. And then as we discussed in the previous lecture, these are not sufficient. These two for equilibrium are not sufficient. These are good for a particle, but not good for a rigid body. If a rigid body wants to be in equilibrium, you need to have a third equation. That third equation is sum of moment is equal to 0. Because we are talking in 2D, the moment is about z. Again, we don't put that z there, but we know it, the moment is about z. Now, if this pen wants to be in equilibrium, I need to have forces, reactions, forces. Again, this has to be, again, if I hold it like this, it can rotate, right? It wouldn't stay like this. You see? It's rotating. Now, it wouldn't stand there. So I need to have another force here to cancel out that reaction. So sum of f of x, sum of f of y is not enough. Right now, y is not rotating because it's a fixed point. I'm pushing that, right? Once I lose it, it will start to rotate. So there are different supports that support the system. Now we're going to talk about what types of supports we have. So the first group of supports we have are just single force support. Those look like cable or link. So cable can hold a structure, but you're going to hold it only, it has 1 degree of freedom, only one force. So if a structure connected with a cable like this, if you remove the cable, you can replace it with one force, and that force will be a tension. Now, you cannot push the cable, right? Cable is always pulling, so when you are pulling, it always is tension. So if you have a cable and you want to remove that cable on your free body diagram that we'll discuss in a minute, you have to replace it with a tension. The second one is a link. So what's the link? Link is pin to pin. So if you have a structure that has two pins on two sides, that will be a link. So if you have a link like this, and that link is connected to my structure, again, this is the structure and this is the link. In this case, if I want to remove the link, I can replace it with one force. Remember, link allowing the rotation, right? It allows the rotation, it has only one force. So I can replace this with one force, either this way, either the opposite way. Again, I don't know the force is in tension or compression, but whatever way you put it, you are correct. In our calculation, if you get a negative answer, meaning that the direction was the opposite way. So this is the first group of supports, either support by a link, either support by a cable. So I'm going to just show you briefly what do I mean with a link. Like for instance, BC in this example is a link. It's between two pins. It's supporting the beam up there, right? So if you remove this link, you have to replace it with one force. I have another example in my hand, which are cables. Now, if you look into the structure like this structure is supported by two cables. One cable here and one cable there. So this the second category of supports are supports for normal. They create normal forces. And those supports are either smooth surface, could be roller, could be rocker. Roller, rocker, smooth surface, they have only one reaction perpendicular to the surface, right? So what do I mean? I mean that if you have a surface like this, and in this surface you have a roller connected to a structure, right? They may look like a joke to you, right? A roller connected to a structure, but they are real. Like if you look at bridges, in many bridges they put a piece of rock. They call it rocker, but the structure of it looks like a rock that rocks onto the structure. So something like this. That's a rocker. That's a roller. Or simply a smooth surface, right? If you have a structure that smoothly stay here with no friction. In all these three cases, I have one force, and that force is perpendicular to the surface. So if this is the surface, this will be perpendicular to the surface. And that's why we call it normal. So a smooth surface, rocker, and roller. For these three cases, I'm going to have one force, and that force perpendicular to the surface to the object. We are talking about reaction, right? Sitting on the chair is all the way up to the person, to the object. Now down here there is one force, force, and force. This is the second category of support. Moving on to the third category of support. If you have a pin, so if you have a pin connected to a structure, so for instance, a pin connection for something like this. Okay, this is the object, a pin connected. So the pin will allow for rotation, right? But you cannot move it in X, you cannot move it in Y. So that's why you have two reaction forces for a pin. If I remove the pin, I'm going to replace it with F of Y and F of X. Again, I put them randomly this way. It could be the other way around, right? But if you, when you calculate them, you get them negative, meaning that the direction of them would be opposite. Usually we don't put AFX, AFY. Depend if this point called A, we put AX and AY for simplicity of it. So this is a pin connection. The other thing that we could have a support of collar. So if you have a structure like this, and in this structure you have a collar. And this collar allow with rotation, right? So you have things like here that allow for a rotation. So this collar can move up and down this way. The handle can rotate. So you're going to have one reaction force, and that reaction force is perpendicular to the rod or perpendicular to the collar. So one F here, that's called a collar. The collar, the handle can be fixed. If the handle is fixed, you're going to have reaction moment because you cannot rotate the handle, right? So if this is pin, okay, but if I draw the same structure and I have a collar here, but this time this thing is welded here, right? Is welded here, so you cannot rotate the handle. If you cannot rotate the handle, you're going to have a reaction moment here, and along with that, force. So losing degree of freedom. You cannot rotate, there's a reaction moment. This thing, you cannot move, it can move up and down, but it cannot move perpendicular to it. Losing 2 degrees of freedom. Now when we go to 3D discussion, you have like also 6 degrees of freedom. Here we have 3 degrees of freedom. You become limited, right? Become limited like this. It can just go one direction. This one cannot rotate, right? And it can go in only one direction. So you have 2 reaction forces. Assume something glued like this. We call it fixed support. If you have a fixed support, can you move it in X? No. Can you move it in Y? No. Can you rotate it? No. You're stuck. You can do nothing. So in this case, I'm going to have F of X, F of Y, and a reaction moment. So in a 2D plane, your support have to have 3 degrees of constraint, meaning that it should be constrained that it doesn't move. If you have a structure and your structure is glued, it's not going to move, right? Like the structure that a minute ago we saw in the question that we solved. Like in this question, the whole thing is fixed on the wall, but it cannot do anything. It cannot move down, up, or rotate. It's just fixed. And this is a rigid body. It's not gonna bend, or nothing else can happen to it. But in this case, you have 3 reaction forces at point A. So the next topic would be the idea of free body diagram. So we talk about supports. Now what would be a free body diagram, and then how can we draw it, or how can we focus more on it? So let's look at this example. In this example, I have a beam, and that beam is pin connected at point A. So that's what the question tell me. It has a pin at A, and then we have a 2-force truss BC. So BC is the link. Keep talking to me. Now I want to draw the free body diagram for this. So to draw the free body diagram, I'm going to separate the part. So let's separate the part. I'm going to put external force and moment on it, whatever was from before on it. So I can see at distance of 1, I have 600 Newton going down. At distance at the end of it, I have 800 Newton. And then I have 900 Newton external moment here. Newton meter. External moment here. Then the beam doesn't have any weight, so I don't need to be worried about the weight of it. It did not give it to me. The only other force I have one force at B, right? And I need to talk about A. The A is pin connected, meaning that it allows the rotation. Now, why the object doesn't rotate? Because of the BC. It doesn't allow the rotation from there, right? But at A, it allows the rotation. So I'm going to have AX here and AY. So why I put AX and AY? Because this is the pin. Now at point B, I have the force FBC. I'm going to call it FBC, or I can call it FCB. That's the force is coming from C to B. Now, can I put it the opposite way? Of course I can, because I don't know what the direction of it is at this moment. But again, I assume it this way. FCB is this way. Now the only thing I need to know, I need to find the angle here. Okay, once we find the angle here, I can solve this, right? I draw the free body diagram for it. How many unknowns I have in this page? I have 3 unknowns, AX, AY, and FCB. And I have 3 equations, sum of f of x, sum of f of y, and sum of moment. So to find the angle here, phi, I'm going to find the angle here, phi. So phi is equal to tan inverse of 1.5 over 2. And I'm going to get 36.9 degrees for it. So the phi is 36.9 degrees. Now, if I want to write the equation for this, equation of equilibrium, first thing I do, we go with these steps, right? I'm going to write the equation f of x equal to 0, sum of f of y equal to 0, and sum of moment about any point is 0. But what point I'm going to select? I'm going to select the point with most unknown in there. Why? Because you're going to cancel all those unknowns into your equation. If I do moment about point A here, that's perfect. Right? I told you moment about any point is 0. I'm going to select point A because it has the most number of unknowns. So now I can write the equation for equilibrium and I can solve it. Before I move ahead, I need to break down FCB into x and y components. So down here I'm going to get FCB sine 36.9. Over there I'm going to get FCB cosine 36.9. So this is the equation on the x. On the x I have AX plus FCB cosine 36.9. Okay, what else I have on the x? Nothing else. This is equal to 0. On the y I have AY plus FCB sine 36.9, which is this one, minus 800. I'm good with that. So let's go back to the most difficult equation for the moment. So moment at point A, AX, AY, no moment. They are dead because they are already in that point. I'm going to be left with the rest of them. The 600, the distance for 600 is 1 to the point A. So it will be 600 times 1, and that's actually clockwise. So I'm going to put a negative here. The next one, FCB cosine 36.9, which is going through the point, no moment from that. So I'm going to be with this, I'm going to be living with that. So will be plus FCB sine 36.9, that's on the y. The distance for that is 2 into, and then minus 800, and the distance for the 800 is 211, will be 4. And then you have a 900 external moment. So I'm going to add that to my equation. Minus 900 equal to 0. Now, in order to solve these three unknowns, three equation, easiest way is that I'm going to start from this equation, right? Solve for FCB. Once I found FCB, I can put it in this equation to find AY, put it in this equation to find AX. So to do that, you can actually continue with the rest of it to do the calculation. So